Okay, so here we go. Last time we were talking about higher order partials, and again, the basic idea of higher order partials is really not that big a deal. If you have a function, you can take its derivative. The result is another function, and what can we do with functions? We can take another derivative of them. It's not a sophisticated point, right? So again, easy examples. There's an x partial, there's a y partial. The results indeed are functions that you can then take other partials of, right? So very straightforward from a mechanics standpoint, right? Okay, now there is something to notice in we talked about the notation, of course, but there is something to notice in this result. Notice that the y partial of the x partial and the x partial of the y partial happen to be the same. So that's kind of an eyebrow raiser, right? It's a little, I wouldn't go so far as to call it weird, but it's definitely interesting, right? And so the question comes up, is that a coincidence? And no, it's basically not a coincidence. Now, I wouldn't go quite so far as to say that this will always happen, because it won't. But almost always. And in Bray, let me not overstate it, in almost every category of question that we're going to consider in this class, this will work. So let me get to the punchline, and then I'll go back and talk about the conditions in just a moment. This is a fancy way of saying that you can put these partials in whatever order you like. Right, that you can move them around in whatever order you like, and it makes no difference in terms of the result. It, of course, does make a difference in terms of what it says that you're doing. The act of taking an x partial and subsequently taking a y partial is a different act than the act of taking the y partial first and taking an x partial after that. So I'm not saying flip them around and it's meaningless, right? It still means something, but you will get the same answers either way if certain conditions are met. And the condition is you need to look at how many partials are you talking about, k in this case, and the function has to be what we call ck. All right, now what does ck mean? Ck means that the function has the feature that all of its partials up to kth order, they all exist and they're all continuous. Now, if you were going to do this with the fourth derivatives of some function of 5 variables, that's a tremendous number of different partial derivatives that you would have to compute and confirm that they exist and confirm that they're continuous, and that would be a lot of effort. Right? And the good news is that most of the time that's not necessary either, because certain categories of functions, their partials are always in that same category, like polynomials. Right? So if you have some great big polynomial, all of its partials, all the way on down, no matter how many partials you take, always still polynomials, which always exist and which are always continuous. So this is not as hard to check as at first glance it might sort of appear to be. So anyway, most of the functions that we're going to deal with in this course are not only ck wherever they're defined, but are C infinity wherever they're defined. In other words, you can take as many partials as you want, and the results will always exist and will always be continuous. Most functions we're going to see in this course. Okay, so nice little punchline. This little coincidence will, practically speaking, in this class is always going to work out. Okay. All right. So good stuff. Now what does this look like geometrically? It's one thing to be able to take a higher order partial. It's another thing to have any use, right, for that higher order partial. And if we're going to use ideas, we need to know what they look like, generally speaking. So let's talk about what a second partial looks like. And I'm going to start by considering the second partial with respect to x. This is exactly what you would hope. Keeping in mind that when we say second partial with respect to x, that means I'm going to take the x partial, and then I'm going to take the x partial of that. Notice in both of which y is going to be viewed as a constant. So y is going to be viewed as a constant for this whole computation. I can look at the entirety of the question of what does the xx second partial look like as happening in this plane where y is a constant, because it is, as I compute fxx. And of course, all other than holding y constant, the only thing you really do when you're taking the xx second partial is you're taking a second derivative of the resulting single variable function. And we already know what that looks like. Second derivatives means concavity. And for example, as you can see here, that as it turns out, this function, that's clearly concave down, and that means that this fxx is negative. Like I say, exactly what you would hope, right? Analogously, I'm going to leave the details of thinking this through as a nice exercise for y'all. Again, I encourage you to do this. What about fyy? Well, x is going to be constant for that whole thing, which means we're looking just at this cross-section of that Pringle-looking graph, and that's concave up, and so fyy, according to this picture anyway, appears to be positive. Everybody all good? Okay. Now here's where it gets a little tricky. We got lucky in this little study that we are just finished looking at, that we were taking the second partial with respect to the same variable. One of the variables was just always constant. Nice, easy connection then to a single variable. What if, though? What if we're talking about a mixed second partial? And very importantly, there is no single variable analog of this. Right? There's a strong connection back here to single variable calculus because ultimately it kind of is a single variable second derivative. Right? This is not. There's nothing like this in single variable. So we can't sort of like lean on, well, it's going to be morally like single variable. No, it's not. Right, so we're going to have to kind of reinvent the wheel on this. And here's the approach I want to take to make this kind of make geometric sense. When we're taking the x partial of the y partial, I'm going to look at the first one computed, partial with respect to y in this case. That first partial that I'm doing, I'm going to interpret as a slope of the graph. Because I can draw the graph of that function I'm taking the partial of. So slope of the graph will be how we think about the y partials here. But now, next question, can I think of the x partial as being like maybe slope of the graph in the x direction? No, I cannot. Because I'm not taking the x partial of f. I'm taking the x partial of this totally different function called the y partial of f, and I don't have a graph of that. Presumably, I'm looking at a graph of f. The y partial of f, I don't have a graph, and if I'm not looking at a graph, I can't use graph interpretations. Right? So a very, very different scenario here. Is everybody comfortable with how we have to? Okay. So, how am I gonna make sense out of x partial if I can't look at a graph? And I'm gonna use, wrong color. I'm gonna use this other interpretation that says, x partial means how fast is this thing changing as I move in the x direction. Right, this is kind of our the interpretation we had of a partial for the literal picture. Right? As you're moving in the domain in the x direction, how fast is this object of the x partial changing? Okay, so here's a picture of that. Here is a graph of some function f. Well, I didn't draw the surface itself. You could probably imagine that when we're looking carefully at a bunch of different slopes on a single surface, the picture gets really hard to draw in a way that's easy to visualize. So what I've found is that the best way to visualize this is just not to draw the underlying surface itself at all. And I'm just going to say that these lines here that I've drawn sitting up here in space. These lines are slopes. They are tangent lines in the y direction at these various points on the surface that I did not draw. Again, because it would just make the picture muddled. Right? So each one of these things is a tangent line in the y direction, and therefore each one of these slopes represents a y partial of the function whose graph I'm not drawing. Is that cool? All right. So that's what the y partials look like. The y partials are these slopes. Okay, cool. The x partial then just says, all right, I want to know how are these slopes changing as I move in the x direction. So that's why I drew a bunch of these y partials. I'm going to need to understand how these slopes are changing as I move this way. And now let's just kind of walk through it. By the way, just for kind of hand-waving visualization purposes, you can see this slope back here as I go in the y direction. This is a conspicuously negative slope. It looks like about a -2 to me. So a highly negative slope back here. And then as I come out of the screen, those slopes are doing like this. Right? So into the screen, it's negative. As I come out of the screen, it's becoming more positive. Right? So back here, it's like -2, and then here it's like -1, and here it's like -0.5, and then here it's like 0 or something, and then here it's starting to look positive. And now I ask, rhetorically, how are these slopes changing as I move in the x direction? And, well, they appear to be increasing. Does that make sense to everybody? So if, for a function for which the corresponding picture, and again, I'm not drawing the graph itself, but imagine there's a graph under there. If this is what the picture of the graph would look like and the resulting cross sections, etc., these y partials are increasing, which means the x partial of the y partial is positive. So this is a picture. Let me zoom it. This, in effect, then, is a picture of what it would look like for the x partial of the y partial to be positive. Roughly speaking, kind of that right there. And now I'm going to geometric appeal. I mean, how would I describe this picture? What's the punchline when the slopes in the y direction are changing like so as I move in the x direction? And so this picture right here, like see what I'm doing with my hand right here, I'm going to say that looks like I've got kind of a twist in the surface. Let me not get in front of myself, but kind of imagine I'm holding a sheet of rubber, right, between my 4 fingertips here and putting a little twist in it. Everybody kind of see that? Okay. So, unmixed second partials look like concavity. Mixed second partials look like a twist on the graph. And again, this is, all together what we're looking at is the graph of the function whose mixed second partial we're talking about. Okay. All right, so that was weird. And again, notice unfamiliar, entirely unfamiliar. There is no single variable analog of this, so this is just a new idea. And welcome to multivariable calculus. There's going to be a lot of that. Okay, moving along. Let's talk about parametric curves. And just a quick reminder, we've talked about the calculus of graphs somewhat. We've talked about the calculus of level sets. It's pretty different. The calculus of the literal picture has its moments, and that's also a little different, I suppose. We have not really talked about the calculus of parametric curves. So that's what I want to do now. Now, you're going to notice that this puts topics a little out of order. This gets us into Chapter 3 all of a sudden, when we're not done with Chapter 2 yet. This is another one of those bouncing around things that I talked about at the start of the term. I won't just go straight through the book. I think there's a really nice value in this point of view of the calculus of parametric curves, that's going to have big payoff when we get to section 2.5, which is coming up momentarily. Okay, so I'm going to do the section 3.1 a little early, like so, and then we'll go back into the chapter 2. Okay, so recall what a parametric curve is. Parametric curve, position as a function of time. So it's a function from R1 to Rn. We've seen several examples. Okay, so we know how to write down the derivative matrix of such a function. Okay. Side note, had I not ever thought of derivative matrix, had we just come straight to this, first cat out of the bag, right? When we started doing calculus, and if we had asked, what is the derivative of a function that looks like this? I don't know anything about derivative matrices. I don't know. Can I take a derivative of something like this? This right here is what we would. Whoa, wrong end of the pencil. This is what we would have written down optimistically, hopeful that it might make sense, and it does. There's kind of, in some sense, no reason that you can't just take a regular, good old-fashioned Calc 1 derivative of this function, because everything here makes sense. Position on the parametric curve at time t, cool. Position h seconds later, fine. Those are two different positions, two different vectors. I can subtract them. I can divide by the scalar h representing how many seconds later, or whatever unit of time you prefer. I can do that division and talk about the limit, but it all makes sense. There's no problem. And so, interestingly, now we have kind of, in some sense, two different notions of derivative, and big surprise, we kind of get the same answer either way, right? So I'm going to call this kind of this is an interpretation of the derivative matrix in this context. You might also view it as kind of what's the word I'm looking for? Validation of the idea of a derivative matrix. It produces a familiar result in this context of parametric curves. Okay. Now, what does it look like? Right? If we accept that a derivative matrix is basically a derivative vector, what does that vector do? Now, here's another warning about context and keeping track of what kind of a picture you're looking at. This expression right here, most of our familiarity with that expression is in the context of graphs. Right? And we know that this, in the context of graphs, the version of the single variable version of this, real valued, no vectors. If we're talking about graphs, then it's a slope, and that's our, comfortable point of view. But very importantly, we are not here talking about graphs. When you have a parametric curve, you are not looking at the graph. It's not, right? We're looking just only at the points in the target that come out. We're looking at the image of the function, not the graph of the function. When you draw a parametric curve, position as a function of time, t, there is no t-axis. Right? Look back at every parametric curve we've ever drawn. There's no t-axis, right? So not a graph. Now, with that heavily emphasized, I'm going to ask then, well, how do we make sense out of this expression here? If we can't say slope of the graph because it's not a graph, what can we say? And we're going to kind of reason through this in a morally equivalent way to how we did in Calc 1 class. This represents a location on our now parametric curve. This represents a location a little further down on the parametric curve. And then if I look at, let's see here, color choices. If I look at the difference, okay, a difference is a subtraction. is a displacement, you might say, right? If I divide by h, dividing by h is going to change the magnitude a little bit, making it a little shorter. Well, I'm going to say shorter, right? It makes it a little shorter if h is above 1. But as h gets smaller and smaller, these displacements here, right, the points are closer and closer together along the curve, and once h is less than 1, the division actually makes it larger again. Right? And then in the limit, let's see, do I have reasonable colors? I guess I'll just use black. How about that? In the limit, altogether, wanting to make sense out of altogether that derivative, we're going to look at these dark blue vectors, and you can see as that point gets closer and closer to the first one, they're just going to kind of slide, they're going to kind of turn around to the right, and you're going to get these vectors here like that are increasingly closely tangent to the parametric curve. All right, so that's the big idea. Now, that does, in fact, sound kind of familiar, right? Derivative, tangent, isn't that exactly the same as what we talked about in Calc 1? And no, not quite. In Calc 1, it was the slope of the tangent line. Here, in the parametric curve context, in other words, looking only at the image, not at the graph, there's no slope. It's not a slope and there's no tangent line. It's just a tangent vector itself. It's tangent vector, not tangent line, not slope of the tangent line, just a tangent vector. Is that cool? Does everybody follow and see the difference? Everybody all right? Okay. Alrighty. Okay. So now, what can we conclude about this? So what I'm going to say physically, like what does this remind us of physically? Being as it is a tangent vector. Tangent vector means that it's pointing in the direction that the curve is going. Just a kind of a slangish way to describe tangency. Okay. And now let's think about what the magnitude of this vector is. Well, the magnitude, if I were to take, as I have here, the magnitude of that derivative vector, I'm going to basically sweep some formalities under the rug. It turns out you can move the magnitude onto the inside. There's some formalities that have to be worried about, and the function has to be appropriately regular. That's not our problem, right? And if you think about it, that I have right there, magnitude of the difference vector is just that distance. Let me do it like this. Yeah, there we go. This the magnitude in the numerator is literally just the distance, and this denominator here. Let's see. Here, let me do it like this. That's the distance. This denominator here, that says how much time has passed. That's the elapsed time between moment t and moment t plus h. Right? Oh, typo. Sorry, this should be an h. Make sure to correct that in your notes. H down there. So altogether, what we're looking at is distance per unit time, and that's another familiar physical concept. Distance per unit time is speed. Right? So really nice punchline there, and we can put these two observations together. This thing, the derivative of a parametric curve, is a vector that points in the direction you're going and whose magnitude is the speed, and that's a familiar idea. That is the familiar physical concept called velocity, and again, for color purposes, Velocity. So really nice, very important punchline then for how we're going to make sense out of the idea of a derivative of a vector-valued function when there's a single input variable, which we're viewing as a parametric curve. In that context, derivative of a parametric curve, velocity. Which, by the way, also might sound, give me 2 seconds, might sound familiar. You may recall that there were some examples that they like to do in Calc 1 classes where they talk about, suppose you have a function that represents how you're driving along the road, and they actually talk about how, in this case, derivative is velocity. What they didn't say is that when you're looking at position as you drive along the road in a Calc 1 context, that's literally giving you location as a function of time. That was a one-dimensional parametric curve. So this is really just extending an idea they never really quite finalized in the first place. Yeah, sorry, go ahead.
After you said that should be in H, you then said distance per unit time.
Yeah. Well, that's right. So we started at time t, and then we're ending at time t plus h. And the amount of elapsed time between these two values of time, the difference is h. So that's what I mean by elapsed time. Yeah. And the fact that you asked the question is probably why I wrote t here in the first place. Yeah. But I think in this context I should have written h. Yeah. Everybody happy? All righty. So, by the way, very similar argument you can make in the same sense that velocity is the derivative of position. Likewise, acceleration is the derivative of velocity. Again, a very analogous, write down what the derivative of velocity would look like geometrically, go through an analogous bit of reasoning, and then recall, oh yeah, wait a minute, that's exactly what acceleration is. Okay. All right, so let's do an example. This example should look very familiar. This is just a vector-valued version of something you did a million times back in Calc 1. And that is that if you know the velocity and the starting point, then you can take derivatives and antiderivatives to find position and acceleration. Like I say, it's in single variable, this is just straight up just a matter of doing it. And it's totally just a matter of doing it here as well. If I know the velocity, how would I compute the acceleration? Well, the velocity, I would just take the derivative of it to make the acceleration. And you take the derivative one component at a time. Easy calculations here. The derivative of that is that. The derivative of that is that. Boom, done. Now, a little bit more annoying, going the other way, keeping in mind that we are given the velocity, how would I sort of reverse engineer position? And you got to just think it through and make sure to always get it straight. It's easy to get this backwards, so be careful. Give the 2.5 seconds as necessary to comfortably think, okay, wait a minute. Velocity is the derivative of position. That means position is the antiderivative of velocity, right? So, like I say, it's real easy to get that backwards, so be careful. And so here again, it's just kind of a matter of doing it. How are we going to take an antiderivative of a vector-valued function? Well, we do derivatives one component at a time, so likewise we do antiderivatives just one component at a time, exactly as you would sort of expect and hope. And so let me take this opportunity to remind y'all that Calc 2 is a prerequisite. It's in the prerequisite trail for this course, so it is expected and assumed that you're proficient with Calc 2, and so I'm going to assume that you're good with how to take standard antiderivatives. I am going to promise that we're not going to do anything obscure, right? So like when I took Calc 2, like I had to know how to do the antiderivative of inverse hyperbolic cosecant, right? And then it's never come up in my life since then, right? And so that kind of stuff, no. but I absolutely expect that you are good and freshly polished on substitutions and integration by parts and what I'm going to call trig integrals, by which I mean like if you have integral of sine squared of x times cosine cubed of x, yeah, you need to know how to do that one. It's just you need to remember what the little tricks are, and there's just a couple of little ins and outs, and make sure you're good to go with all that stuff. And all the other standard stuff, like you need to know that how to do integrals of exponentials, right? Stuff like that. Okay. All right. Okay, now, of course, as with always, when you do an antiderivative, plus c. Don't forget the plus c. Let's see here. Here we go. A lot of students mistakenly think that the plus c is always whatever the initial condition is. Very common belief. This is wildly nonsensical. The reason that students have fallen for this is because in a lot of high school contexts, the only functions they're ever talking about are polynomials, and there's this little quirk of how when you take an antiderivative of a polynomial, there's always a factor of t, and you plug in t equals 0, and that term just disappears every single time when you're talking about polynomials. So there is the illusion then that the integration constant is always the initial value. It is not. And I emphasize, it's not just that you will get wrong answers if you fall for this. It is that your reasoning is garbage. That's really the problem. Right? Again, it's not about the answer, it's about the reasoning. And the assertion that these two things must be equal is outrageously unfounded. Just doesn't make any sense. So let me show you how this actually goes down. There's actually nothing to it, really. It's pretty straightforward how to deal with this. All I'm going to do is take this equation here with these three terms, and I'm going to plug in t equals 0. I'm going to plug that in to all three terms in that equation. No big. You plug in t equals 0 into the first equation, and, there it is. It's t equals 0. That's 5, 6, given. Right? You plug in t equals 0 into this equation, and a little bit of arithmetic ensues, and you get 3, 1. And then, of course, nothing's happened to this yet because we need to solve for it, but the c remains the c. But notice, I just plugged in t equals 0, and what I get as a result is an equation in which I can easily solve for what my c is, right? And you can see c, in this case, turns out to be 2, 5, and notice, very importantly, it is absolutely not 5, 6. It's outrageous. Is that cool? Okay. All right. Okay. All right. Let's see here. A quick comment. Very importantly, right now we're talking about antiderivatives. So, for example, when I say position is an antiderivative of velocity, yeah, right? I mean, antiderivative. A lot of people like to say the word integral in talking about an antiderivative. Somebody didn't think that through decades and decades ago, and as a result, it's created a confusion in calculus students ever since. I think it's really important to distinguish integrals from antiderivatives. They're closely related, but it's a big deal that they're closely related. And now, just thinking strategically, if there is an important fact, very important fact called the fundamental theorem of calculus, pretty important fact, that two different things are closely related to each other, if you use the same word to refer to both of those things, then it's hard to talk about the important fact that they are in fact related. Right? It becomes much more confusing. So please don't think about, please don't conflate antiderivatives with integrals. And if you, like me, were brought up mathematically with this sloppiness, then you're probably going to be fighting this problem further, at least until you're my age. I'm still fighting it myself, right? I will sometimes say integral when I mean antiderivative. So anyway, good luck and exert every possible effort to keep that straight. Yeah.
So which one is the one that's the area under a curve?
Yeah, so integral. Well, so if you're in the special context of a single variable function for which you're looking at the graph, and if that function is appropriately regular, then the integral will compute the area under the curve. So here, notice we are not looking at a graph, and it's not a single variable function. So there's really no way to, the idea of interpreting this as an area in some sense, it makes no sense at all, right? Because it just doesn't fit those requirements. Yeah. Right. Okay. All right. So, by the way, if you are maybe not entirely sure on the difference between an integral and an antiderivative, an integral is a Riemann sum. An antiderivative means you're undoing the process of differentiation. Right? Notice, by the way, if you take a function and undo the differentiation, the result is a function. Whereas when you compute a Riemann sum, the result is a value, not a function. So again, they are different things, and again, closely related. And again, the fundamental theorem of calculus is very valuable, very important. But the theorem does not say that they're the same. It says that they're related, and they are fundamentally different as objects. Okay. Alrighty. So. Real quick, the rest of section 3.1, there's a bunch of stuff about Kepler's analysis of like planetary motion and stuff like that, and it's classical and beautiful and historically important, and yeah, sure, but it's not really what we're interested in for Math219. So as much as I would love to do this, if this were a full year course, I'd probably keep that in, but it is not a full year course. We absolutely don't have time for that. So and this is noted on the content syllabus. Don't forget to always keep an eye on the content syllabus. You're not responsible for all the Kepler stuff, right? And you're welcome to pretty much ignore all of that, with one exception, and that is this. Oh, I missed. This theorem here. It's just an observation of something that's kind of convenient, and that is when you're taking derivatives of vector-valued functions, parametric curves are vector-valued functions, right? If you're taking a derivative of vector-valued functions, then the derivative of the dot product of those vector-valued functions obeys a product rule, and likewise with a cross product. There is a corresponding product rule. Again, it lays out on the page exactly as you would hope it would. So this is good news, but do make sure to know this. It can be very handy sometimes. Okay. All right, that's the only part of the Kepler stuff that you have any responsibility for. Yeah?
I remember dot products produce scalars, right?
Yes, that's right.
So if you take the derivative of a scalar...
Yeah, that's right. So this is a scalar valued function. That's right. And its derivative, you'll notice, is a sum of a dot product, which is therefore a scalar, and another dot product, which is therefore also a scalar. Yeah. Yep, totally.
So instead of doing the dot product first, you can just split it first and then do it separately.
You can follow this rule. And yeah, totally. Yeah, exactly. Okay, so on to section 2.5. And I'm going to segue into the multivariable chain rule by reminding you of the single variable chain rule, which I know you know, and I know y'all are all experts at the execution of the single variable chain rule. Prerequisite trail, going to assume it for the purpose of this class, make sure you're good with that, all that business. I'm going to take a very deliberate, narrow point of view on the single variable chain rule. This is arguably, I haven't kept track, but it may be the first example of something I'm going to do a lot in this class, which is kind of build up to multivariable ideas by taking a very specific and particular point of view on the single variable version. And very often, if you look at this, at what you already know, single variable calculus, if you look at it just the right way, then the multivariable extension is very, very similar and very, very, therefore, familiar and hopefully easy to understand. So I do a lot of that in this class. Here's our first example. Y'all have a million points of view on derivatives. Here's the one I want to take here. A derivative relates velocities. So in particular, you could think of x prime as representing a velocity in the domain. You could think of y prime as representing a velocity in the target. And the derivative of f is what you multiply by the input velocity to get the output velocity. Now, this might not be your favorite point of view on the single variable chain rule. Cool. But this is the point of view that we're going to need to make this argument that I want to expand on, to make this argument work. So make sure that you are thinking about, for the purposes of this page of notes, this is how we're thinking about a derivative. It's what you multiply by input velocity to get output velocity. Is that cool? All right. And with that point of view in mind, let's now look at a composition of functions. For example, here's a single variable function. X is the input, y is the output. F is the function that does it. Right? I can talk about the derivative of f as described above, as the thing you do to input velocities to get output velocities, right? No problem. Okay. Right. Now let's look at this function that we're going to sort of tack on to the end of it. Looking only at this function g. G has an input variable called y. It has an output variable called z. And I can talk about its derivative. The derivative of that function g, which I might write as dz dy, that's what you multiply by input velocity, y prime, to get output velocity, z prime. So same idea, just applied to a different function now. And then I can also think about the composition itself, which has x as the input, z as the output. This composition itself also has a derivative, which I'm going to write as dz dx. And that derivative you interpret in exactly the same way. It's what you multiply by input velocity, this time x prime, to get output velocity, this time z prime, if you're talking about the derivative of the composition. Is everybody on board? Everybody happy? Okay. All right. So, when you stick two functions together, there are three functions to talk about. There's the original two, and then there's the composition. So now I'm going to first kind of wave my hands at the algebraic sort of point of view on how to combine all this together and get a familiar result. But there's different ways to think about this. I'm going to observe that if you take this formula for y prime and stick it into there, then you get this algebra. Right? We have a formula for y prime. Let's stick it in here where it also says y prime. That's all I do. Okay. Now, next, let's take that result and compare with this number 3 up above here. And you see both of them tell me that there's something I can multiply by x prime to get z prime. See, something I can multiply by x prime to get z prime. And that means that those two somethings are the same. And so when you do that, this and this must be equal, and thus there's our chain rule. Single variable chain rule. Is that cool? Now again, you don't have to, the algebra is not really the point here. The point is that this is a perspective that allows me to derive a familiar old result. Okay, now let me give you a different way to think about this process and this result. I mean, if what a derivative does is turn an input vector into an output vector, and what I do to turn this x prime into this y prime is to multiply by a factor, right? Here I multiply by a factor, and then here I multiply by a factor. Altogether, when you multiply by a factor and then another factor, altogether you multiply by the product of those two factors. And that's, I think, a pretty reasonably satisfying alternative point of view on this equation. If you have some number, if you multiply by 2 and then multiply by 3, that's the same as multiplying by 6. That's the same as multiplying by 2 times 3. So, same idea here. Okay. All right, so you get this familiar form of the chain rule. There's this nice pithy little summary that differentiation turns a composition into a product. Right? When you compose functions, you effectively multiply the derivatives. Right? Again, old news, I hope. And with all of that reminded, let's now do the same thing for multivariable functions. Now again, we have a bunch of different points of view on what a multivariable derivative does, and I'm going to take again a very particular narrow point of view for the purposes of extending the analogy. A derivative is a factor. It's what you multiply by input velocity to get output velocity. Now, it's slightly different, to be fair, right? I mean, in single variable, it's a scalar factor. Here, it's a matrix that you multiply by input velocity to get output velocity. Yeah, sure. Okay, so it's different. But it's still a factor. It's the thing that you multiply to turn input velocities into output velocities. And now, armed with this point of view, let's again sort of compose a couple of functions. Notice we have here a function. The x variables are the inputs, the y variables are the outputs. Here's another function. The y variables are the inputs, the z variables are the outputs. And again, just like in the single variable case, you can talk about composing them, where the x's are the inputs and the z's are the outputs. And again, you can do this algebraically or sort of intuitively. Let's do the algebra first. Taking this formula for y prime and plugging it into there gives me this. That's just a matter of plugging it in and writing it down. No big deal. Again, I can compare this equation with the just direct interpretation of what the derivative of the composition does. It turns x prime into z prime. And just look at that and look at this. That means that these two things have to be equal, and thus we get our multivariable chain rule. All right? Multivariable chain rule. So if you have two functions, if you have a multivariable function f and a multivariable function g, and if you compose them together, what comes out of f goes into g, just like I have in this drawing here. When you do that, you produce a composition, g compose f, and the derivative of that composition is the product of the individual derivatives. Again, I think the little pithy summary is really nice. Differentiation turns a composition into a product. Is that all right? Everybody on board? Okay. Real quick, I want to let's see. Actually, how are we doing on time here? I have 13 seconds. Okay. Man, I guess I won't be able to make my point. I'll pick up here on Wednesday. Y'all have a good rest of your day. See you later.